We are in chapter 4 where we are discussing bending. This is the 31st session, and here we'll look at eccentric loading. This is a look at the overall sessions covered in the first 4 chapters before we start discussing the session at hand, which is eccentric loading. As we can see, we are in the last leg of our discussions involving bending. We start looking at eccentric loading. It can also be considered as a combination of axial loading and pure bending, as we shall find as we move forward. This is a cantilever beam with a rectangular cross-section, and this is the axis of symmetry, and this is the centroidal axis perpendicular to the axis of symmetry. The eccentric load P is applied on the axis of symmetry at a distance A from the centroid. These are two equal and opposite forces which are parallel to P and has the same magnitude P acting on the centroid. The loading here and the loading shown in figure 1 can be considered to be statically equivalent, since all we have done in figure 2 is add two equal and opposite forces. Now these two forces can be considered as a couple. So these three forces can be considered to be equivalent to a force P acting on the center or the centroid and a couple PA. So as mentioned earlier, an eccentric load can be seen as a combination of an axial load and a moment. This case and this case are statically equivalent. Earlier we had considered a bar subjected to an axial force independently, also a beam subjected to a moment independently, as well as circular bars subjected to torque. We had mentioned that these types of forces can be combined, and here is the first combination where we have axial loading and moment acting at the same time on a beam. Consider a section perpendicular to the axis of the member. Then there is an axial load acting, so there would be compressive stresses in the section. There's also a moment acting, so there would be bending stresses on the section. The net stresses in the section is given by algebraically adding the stresses due to the axial force and the stresses due to the moment. Consider the diagram from the previous slide as shown here. This is a cantilever beam, rectangular in shape, and there's a load, axial load that acts on the centroid and a positive moment that acts on the beam. Now let us consider a section CC as shown and find out the variation of stress on the axis of symmetry of this section. Due to bending only, the stress variation is given as sigma bending is equal to minus my divided by I. Due to the compressive force, sigma axial is given as minus P divided by A. It is uniform along the axis of symmetry and does not depend upon Y. So the algebraic sum of stresses on the axis of symmetry on the section CC is given by this expression. We now look at the variation of stresses using stress diagrams, again on the same axis of symmetry. So because the moment applied was positive, the section CC, or the axis of symmetry on the section, would have compressive stresses on the top and tensile stresses on the bottom. Due to the compressive axial load, there will be uniform stresses that are compressive in nature, acting on the same axis of symmetry. Adding these two up algebraically, we get this variation of stress. We notice that the neutral axis, or the axis of zero stress, has shifted downwards from the centroidal axis, which in the earlier case of only bending coincided with the neutral axis. This diagram shows the stress variation on the axis of symmetry of this section, but the stresses will be the same if we take any other axis parallel to the axis of symmetry. So this gives the variation of stress on the whole section. Here again we see that the neutral axis of the section has moved downwards from the centroidal axis. In case the direction of the moment was same and P, instead of being a compressive axial load, was a tensile axial load, then we can imagine that the neutral axis would have moved upward instead of downward compared to the centroidal axis. In the earlier slide, we considered a compressive axial load acting on the centroid. Here we have a tensile load acting on the centroid. In the earlier slide, the moment was positive. Here also the moment is positive. For this case, here we have the expression for stress. With both load and moment positive, this can be also considered as the algebraic form. If the centroidal load is negative, then we have this form which we saw in the earlier slide. If the moment is negative, then we have this form. If the centroidal load and moment are both negative, then we have this form. Here we look at examples. This is a clamp, and here there are two forces P acting. The allowable normal stress is given, and we are asked to find out the maximum value of P that can be applied. A portion here will be subjected to maximum stress. So we take a section A. We can find the forces acting on section A by two ways. We can consider equilibrium of the portion left of A. Then, since there's a force P acting here, there must be a compressive force acting at the section. Also, this load P and this load P make a couple, so there must be a moment acting at A. The other way is to take a section such as PP and consider two forces of equal magnitude acting. Then this loading is equivalent to this loading. These three forces result in a compressive force and a moment acting at P. Now, considering equilibrium of AB, an opposite force and moment will act in the section A. As we see, the two different ways give the same result. With the area of the section known, we can find out the compressive stress acting at A in terms of P. In this equation, we can write the moment in terms of P. We can then find the maximum compressive and tensile stress acting on the furthest fibers in the section A using the equation. Since the load here is compressive, the maximum stress in magnitude with the compressive stress, which we can write in terms of P. We are given the maximum allowable stress, which we can equate and find out the value of P. Here we have a problem involving eccentricity. This load P, whose magnitude is given, is applied at the centroid of this face. We are given the maximum allowable stress and required to find this depth P so that the material does not fail. We take a section A. This portion of depth P is shown in this diagram. The section is subjected to a tensile force and a moment. Since this dimension is d by 2, the moment acting will be P bracket 35 minus d by 2. The moment is negative. We'll find the maximum stress in this portion due to the loading and equate it to the maximum allowable stress to determine D. The maximum tensile stress due to P is equal to P divided by 70D. The maximum tensile stress due to bending occurs at Y is equal to D by 2. So we have substituted D by 2 for Y, and I is the I of this section. Rearranging, we get the maximum tensile bending stress in terms of P and D. The total maximum tensile stress will be the sum of these two, which is given here. This will be equal to the maximum allowable stress. Substituting P, we get a quadratic equation in terms of P, from which we get the value for D. Here we have a case of eccentric loading. The shape of the structure we are considering is unusual. It is she-shaped, as we can see in this diagram. This is the side view of the structure arrangement as well as the load. If we take a section AA, then this is the plan view. The load P acts as shown, and in the plan view, it acts at this point. We are given the allowable stress in tension and the allowable stress in compression. We are asked to find the value of the load P. So given where the load P acts and the geometry of the structure, we can find out the maximum tensile stress that acts on the structure in terms of load P. We can then equate it to the allowable maximum tensile stress and get a value of the load P. Also, since we know what the load P acts and the geometry of the structure, we can find out the maximum compressive stress that acts on the structure in terms of load P. We can then equate it to the allowable maximum compressive stress and find another value of load P. We can then compare these two values of load P, and whichever is the lesser will give us the maximum value of the force P that can be applied without failure. To start with, we find out the position of the neutral axis. We find it in terms of the base axis CC. The geometry is divided into three rectangles, two rectangles that has been denoted 1 and one rectangle that has been denoted 2. The distance of the centroid YC is given as summation AI yi dash divided by the total area. Here we have rotated this diagram by 90 degrees. Now we know the position of the neutral axis and we can find out the moment of inertia of this section. So we find the moment of inertia of these three rectangles about their own centroidal axis and then add AD square to find out the moment of inertia about the neutral axis, which is given here. A load P acts on the structure as shown. As earlier, we have added two other forces P acting on the centroid that are equal and opposite to each other and parallel to the force P that was already acting. So now we have a tensile force acting on the centroid as well as a moment. Let us take a section 1-1 of the structure and we consider equilibrium of this portion. Then at the section 1-1 there will be a tensile force as well a moment acting as shown. This is section 1-1 shown from the top. This tensile force will cause tensile stresses on the whole section. This moment will cause tensile stresses on this part of the section and compressive stresses on this part of the section. So AB will be subjected to the maximum tensile stress, which we have found here by adding the tensile stress due to the tensile force and also to the due to the moment. We have found it in terms of P. We were earlier given the allowable tensile stress, so we have equated these two to give us a value of P. The points E and D are subjected to compressive stress due to bending and tensile stress due to the axial force. Again, we have added these two up and we have equated the compressive stress with the allowable compressive stress. This has given us another value of P. We find that the value of P using the maximum tensile stress is lower. So this is the value of P that can be applied to the structure without failure. Here the problem is the same as the previous problem, except that we apply the load P in the opposite direction. So the geometry of the structure is the same. The point of application of the load is also the same. Also, the allowable stresses in tension and compression have equal magnitude. Since the geometry of the structure is the same, the neutral axis is also at the same distance, and the magnitude of the moment of inertia is the same as the previous problem. The load P acting on the structure acts upwards as shown. As such, we have considered two forces P acting on the centroid in the opposite direction as shown here. This is statically equivalent to a force P acting on the centroid, a compressive force, and a moment acting in the direction shown. If we take a section 1-1 then and consider equilibrium, then on section 1-1 there's a compressive force P acting, and there's a moment acting in the direction shown. Looking at section 1-1 from the top, we have a compressive force acting and a moment acting as shown, so that at AB there'll be compressive stress both due to bending and due to the axial force. The points E and D will be subjected to tensile stresses due to bending and compressive stresses due to the axial force. So first we find the stresses at E and D, which will have the maximum tensile stress in terms of P, and then equate it to the allowable maximum. This gives us a value of the load P. We also find the stress at AB due to the moment and due to the axial compressive force. The stress at AB, which we have obtained in terms of P, is equated to the maximum allowable compressive stress, from which we get a value of P. Now here again we see that the value of P obtained considering maximum tensile stress is lesser, and as such it is considered the value that can be applied without failure. This is a problem that involves strain gauges and eccentric loadings. Eccentric loading is applied on the axis of symmetry. So here we have a cantilever beam with an eccentric loading. The load applied is P and it is at a distance d from the centroid on the axis of symmetry. Two strain gauges are attached at A and B, and we are given the readings of the strain gauges along with the Young's modulus of the material. So essentially we are given the stress acting at A and B. We have two unknowns, E and D, and we are given the stresses at 2 points, A and B. So we can think of forming simultaneous equations to solve for the two unknowns. We can also think of the two unknowns as the axial force and the moment applied. Earlier, we obtained the stress for an axial force applied to a bar, and for a positive axial force, the stress was given as P divided by A. Also, we obtained the stress due to a positive moment, and it was given as minus my by I. Let us consider a section that is perpendicular to the axis, and the points A and B are given on the section along with the y distances as shown. If we consider the point A, then we can see that the stress due to the tensile force will be positive, and also the stress due to the negative moment at A will be positive. Using the proper signs of M and Y, we get the stress at A using this expression. However, we have already obtained the stress at A from experimental values. Equating, we get the equation 1. The two unknowns here are P and Pt, which can also be considered the axial force and the moment. At P, we can see that the stress due to the axial force will be positive, and the stress due to the moment will be negative. Again, putting the appropriate signs and values of M and Y, we get an expression for the stress at P. We have earlier obtained the stress at P from experimentation. We equate these two to get the second equation. Using the two simultaneous equations, we obtain the value of Pt. Substituting the value of Pt in equation 1, we obtain the value of P. These values are obtained in terms of E, the Young's modulus, and substituting the value of E, we get the force P and the distance B. These are the unknowns we were looking for. Here again, we have a problem involving strain gauges and eccentric loading. The eccentric loading is along the axis of symmetry. So we have an I section as shown, and there's a portion on top of the I section on which the loads P and Q are applied. The distance at which P and Q are applied are given, but we need to find out the magnitude of P and Q. Two strain gauges are at A and B, and the strains corresponding to the strain gauges are given along with the modulus of elasticity. So we can find the stresses acting at A and B. With the stresses known at A and B, we can give two simultaneous equations by which we can find out the forces P and Q. Now, as discussed earlier, the force P acting here can be equivalently given as the force P acting on the centroid and a negative moment P multiplied by this distance. Similarly, Q can be equivalently given as a force Q acting on the centroid and a positive moment given by Q multiplied by this distance. We have written the moment associated with E as mz1 and the moment associated with Q as mz2. Earlier we have given the formula for stress for both force and moment acting by this expression. Here we have replaced P by F since P is part of the problem here. Here the force acting is compressive at the centroid, both due to P and Q. So F can be written as minus bracket P plus Q. At this stage, we don't know the sign of the moment. It can be positive or negative. So the moment is written as mz is equal to mz1 plus mz2. We obtain the stress A. So sigma A is obtained by putting in the values of F and M and also Y. So putting all the values, we get sigma A by this expression. The value of Y is positive for the point A, as shown in this diagram. This is based on the coordinate system we have chosen, as shown here. This diagram is the diagram of a cross-section perpendicular to the axis taken through A and B. We already have the stress acting at A from experimental values. So equating the two values of the stresses, we get an equation in terms of P and Q. We refer to this equation as equation 1. We now look at stress at the point B. This was the original equation of stress at a point in a body subjected to both axial force and moment. So here both P and Q are negative, so we get F as minus P plus Q. At this stage, we don't know the sign of the moment, so we write again the stress at P using this expression. After this, we substitute mz1, mz2, and y of point B, which is negative. So substituting all this in the equation for sigma p, we get the expression of sigma p in terms of p and q as shown. We earlier obtained the stress at p using experimental values. So we equate the two values to get this equation, which we have referred to as equation 2. In order to get equal and opposite coefficients in front of q in equation 1 and 2, we multiply equation 2 by this constant value. From the simultaneous equation 1 and 2, we get the value of p. Substituting the value of p in equation 1, we get the value of q as well.